sometimes to determine the number of subatomic particles based on some factors. So protons we got from the periodic table, neutrons we got from the atomic mass or the mass number, and then electrons we use this idea that they have to be balanced out. They have to be even in order to have a neutral atom. You have to have as many protons as electrons. Then we played with that a little bit and said, well, what happens if you don't have the same number of protons and electrons? And we called the result of that ions when there's this imbalance. So today we're going to look at what kinds of ions can you form, or what ions are more likely to form for different atoms. And then if we have time, we'll start putting them together and making compounds out of those ions as well. All right, to figure out what kinds of ions form, we have to construct something called an electron configuration. Basically, where are the electrons in this given atom? And to do that, we have to know something about the structure, about how the electrons are arranged inside the atom. We talked last time about the structure of the atom, and we said it's not exactly right that the electrons are orbiting the nucleus. They're not like planets going around the sun. They just kind of hang out in these clouds around the atom. And what we can say is there are some different levels of clouds. There's a cloud that's really close to the nucleus. There's one that's a little bit further away. There's one that's a little bit further away. And they keep kind of going in these discrete clouds called shells. So if we have the nucleus here with our protons and neutrons, we're going to talk about we're going to focus on 3 of these electron clouds. The one that is closest to the nucleus, one that is a little bit farther out, and one that is a little bit farther out still. And remember, these aren't orbits. These aren't like electrons swirling around in a particular track. These you can think of as like 3-dimensional spheres, kind of these clouds or these shells that the electrons exist within. And they have a certain capacity. There's only so many electrons that each shell can hold. The one in the middle, closest to the nucleus, can hold 2 electrons. The next one can hold 8. And the one after that, we're going to say can hold 8. Really, it can hold 18, but we're not going to get into that just yet. So we're going to say essentially 2, 8, and 8 electrons fit in these different shells going away from the nucleus. Now, which ones do you think are the most stable? Which shell do you think has the most stable electrons in it? The innermost? Why?
Because it has to fill up first.
Yeah, but why? What's special about it being inner? You're right. You're right. I don't know. Anybody? What's special about the inner one? Why would the inner one fill up first? Why would the inner one be the most happy place for an electron to be? Yeah, they're attracted to the protons. Protons are positively charged, electrons are negatively charged. So those two want to be as close as possible to maximize that attractive force. So that first shell is going to be the lowest energy. So what I like to do is graph this, where the x-axis is the distance from the nucleus, and the y-axis is energy. And we're going to talk about 3 different buckets for each of these, buckets that electrons can fit in. A lower energy bucket that fits 2, a middle energy bucket that fits 8, and then a higher energy bucket that fits 8. And those will be our clouds or shells 1, 2, and 3. So when we're trying to figure out where electrons are in a molecule, we're going to fill them up from inner to outer or from lower to higher bucket. So if we count up electrons, like let's say carbon, how many electrons does a carbon atom have? How do we find that out? Yeah, we look at the periodic table. The atomic number in blue is the number of protons, but for a neutral atom, that's also the number of electrons. So we can say carbon has 6 electrons. And then we can start placing these electrons in these buckets from lower energy to higher energy. So 2 fit in here, and then we jump up to the next one, 5, 6. And that's it, we're done. We've got 6 electrons in the buckets. We haven't gotten into that third one yet. That's fine. Let's try another one. Let's look at sodium. How many electrons does sodium have? 11, right. 11 electrons for sodium. So let's fill up the buckets for sodium as well. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. All right, two atoms, 2 electron configurations. So this tells us where those electrons are in those different shells. Now there's various ways you can do this. You'll see in the lab today, it asks you to use the circles around the nucleus that way. I like doing it this way because it also shows the relative energies, so you can see which ones are higher energy than others. And we're going to introduce a couple more terms that help us to develop this idea of what is going to happen to these electrons. What are they going to do with these, to these electrons? What are the atoms going to do with these electrons? So the terms we need to know are valence electrons, the valence electrons are the highest energy electrons. The ones farthest away from the nucleus, the outermost electrons. Why do you think that's an important designation? What do we care? Why do we care what the outermost electrons are?
If they're not complete, they can bond with other ones as long as it completes the...
Right. Those are the electrons that are going to be doing stuff. The ones close to the nucleus are happily held by the nucleus. They're very strongly held by the nucleus. They're not likely to go out and grab other atoms and bond or get rid of electrons or get more electrons or anything like that. They're full, they're close to the nucleus, nothing's going to happen to them. So really only these valence electrons are the ones that do what we call chemistry. Mixing with other things, making compounds, all that stuff. So we need to be able to identify which ones are which. So if we look at our 2 examples here, in the first one, carbon, where are the valence electrons there? Which bucket has the valence electrons?
2.
2, right? Everybody see that? Those are the highest energy and the outermost. So we would say that that is the valence shell and that those are the valence electrons. What about for sodium? Which bucket has the valence electrons in sodium? Sodium's going to have 3, right? And there's just 1 electron there. So sodium will just have 1 valence electron. So this one has 4 valence electrons, and this one has 1. Valence electron. Everybody see how we got that? The other ones are called the core electrons. Anything that's not a valence electron is a core electron, meaning that it's held by the nucleus inside the atom. So this would be core electrons there. For sodium, all of these are the core electrons. So you add up the valence electrons, the core electrons, you should have the total number of electrons. There aren't any that don't fit in one of those categories. Okay. So if we look at the periodic table, look at the groups, the columns that sodium and carbon are in. And look at their number of valence electrons. And tell me if you see a pattern. Ever see anything? What do you see? Go ahead.
Elements in group 1A will have one valence electron,
Yeah.
and then like 2 will have 2.
So it seems to be general across, at least looking at these examples. Yeah, everybody see that? So sodium is number 11. It's in the first column, group 1A, and it has one valence electron. If we move over to carbon, that's in the fourth column, 4A, with 4 valence electrons. So something about that organization has to do with this same thing. And in fact, that's why the periodic table is set up the way it is. Because this way, atoms with similar numbers, with the same number of valence electrons will be right on top of each other. And because that number affects the behavior of the atom, it means that elements in the same group are going to have similar kind of behavior. So that's what we see. That's what we see in the periodic table. And it also really helps us out because one thing that we're going to need to know a bunch today and going on is how many valence electrons are in some given element. And the way you're going to find that out is by looking at the periodic table and looking at those group numbers. Now, it doesn't work for the Bs. There's different systems in place there. But it's a little different there. But it does work well for the A's. So you always have two choices. You can count them out with the buckets, or you can use the column numbers on top. And those are going to apply to the entire column. So if I said, how many valence electrons does sulfur have? What would you say?
6.
6, right? Because it's in column 6. Now we can fill up buckets and count 16. We get the same answer. We get 6 electrons in that third bucket. Okay, so now let's talk about how these things make ions. Has anybody ever seen sodium as an element? What it looks like? You know what it looks like? Okay, let's cue this up. Let's watch a quick video of that. I would do it as a demonstration, but you'll see why I can't do that for a minute. Oh, I gotta change the sound too. Try it again.
I'm recording it.
Okay, so we get to watch this very high-tech video of chemical professionals working safely with chemicals. But that chunk of stuff that he's holding here is sodium. Let me get a better view of it. There. Looks kind of like a whitish thing. It's actually a metal. It makes its own oxide coating because it reacts with the air, and that's why it looks whitish. But when you cut it, you'll see it's actually shiny, and it's pretty soft. You can cut it with a knife. It's a pretty soft metal, but when you do cut it, it has a very shiny surface for a little while, like a few minutes, and then it clouds right up again because it reacts with the air. All right, so we're going to watch some sodium
Wants to throw it in.
getting thrown in a pond.
I will. Here, give me the glove. All right, I'm gonna just keep throwing it.
Oh! Explosion!
I need a slow motion, guys. Hold on.
Wait.
We are recording.
Wait.
Hold on.
You can see all the protective equipment that they're wearing, goggles, and
Sodium.
camera stabilizers.
That's fun.
Ready? That way? There you go. Oh, geez.
Oh, no.
It explodes.
Yeah! Wait, it's not the.
So that's why we couldn't do it in class.
volcano. What
Sorry.
is-
Is that hard? It's sodium.
It's gonna do.
Okay, so that's sodium. Sorry we couldn't do that in class. It would have been exciting, but also really dangerous, as you can see. Okay, so that's sodium metal, the stuff that we've been talking about right here. In the course of that reaction, it's reacting with water to make hydrogen gas, which is why it explodes. It ignites the hydrogen gas. And it's going from sodium to sodium ion. So how many electrons does sodium ion have? If it's +1, if it's a +1 ion. 10 electrons. Because sodium always has 11 protons. So if it has 11 electrons and 11 protons, it's neutral. If it has 11 protons and 10 electrons, it's got a +1 charge to it. So if it has that +1 charge, that changes its electron configuration. If it's lost an electron, and we count up 10 electrons, we now have this kind of a situation. So we saw what happens when you throw sodium metal in the lake. It releases a bunch of energy and becomes sodium ion, which means that this ion must be much lower energy than the metal itself. It must be much more stable because a bunch of energy came out when it got thrown in the lake. So what is this stuff? You have any experience with this ion? Is it also an explosive metal? No, shake your head. No, this is the stuff that's in salt. This is like we talk about sodium chloride, table salt. That's the stuff that's in there. Anybody here taken like physiology, those kinds of classes yet? Talk about all the sodium channels and all the stuff that sodium does in your body. That's about as far as my knowledge of it goes, but it has something to do with nerves and muscles and like everything else. I don't know, you probably know way more about that than I do. But that's all this stuff. That's all this sodium ion, not sodium metal, because obviously we don't explode all the time. So sodium ion. So there's something special about this versus this. Anybody want to guess what it is, looking at the electrons?
Valence shells, 1 and 1.
Yeah, we've changed the electron configuration so that we now have an empty bucket up here and some full buckets down here. And that turns out to be a really important consideration, something that really affects the stability of these materials. The way I like to say it with this particular drawing is we could say, this doesn't really make any sense, but we can say full or empty buckets are happy buckets. So we want to have full shells or empty shells, not the in-between ones. The in-between ones are less stable. And since we have all kinds of every possible different count of electrons from 1 up to whatever, that means most of the elements are going to have not full shells. They're going to have a little bit full or a little bit half full, half empty, that kind of a thing. And so that's going to help us to understand what kinds of ions and what kinds of compounds these elements form. So we could say that any element that has 1 valence electron wants to lose that valence electron so that it has all full and empty buckets. And so those types of ions are probably going to make those types of atoms are going to make +1 ions because they're going to want to lose 1 electron. And so everything in group 1A is likely to make a +1 ion. And that's true. That works out. Let's look at some other ones. And maybe we don't have to draw the buckets this time, but we could look at chlorine. How many valence electrons does chlorine have?
7,
How do you know?
because it's in group 7A.
It's in group 7. Everybody see that? Number 17 over there? Group 7A means 7 valence electrons. So 7 is not full or empty. It's in between. There's 2 possible ways that chlorine can get a full or empty bucket, right? What are they? So we could get one more, or what's the other way?
Lose 7.
Yeah, well, there's that. We'll get to that later. But it could lose 7. So we could say for happy buckets, gain 1 electron, or that's not how you spell over, or lose 7. If it gains 1 electron, we make Cl minus, because now there's 1 more electron than the proton. If we lose 7 electrons, we get Cl plus 7, or 7 plus. So which one do you think is more likely to form? If you had to guess. Cl minus, yeah, why?
It's a lot easier to lose 1 than gain 7.
The other way around, but yeah, right.
Oh,
Yeah. Yeah, we usually go with whatever the smallest number of electron transfer stuff is. So we're probably going to gain 1 and not lose 7. That's going to be easier. Or probably not going to do that. That doesn't mean that it always works out that way, but as a general rule, we're going to go with whatever one means the fewest, the least transfer of electrons. So now, looking at anywhere in the periodic table, and again, this kind of breaks down in the middle, so we'll look at the ends mostly. We should be able to see an element and guess what kind of an ion it's going to be. So if I said aluminum, Al, number 13, what do you think is going to happen to those electrons to get happy buckets?
Lose 3.
Lose 3. Everybody see that? Aluminum's in the third, or in group 3A. So it has 3 valence electrons. So it could lose those 3, or it could gain 5. Since 3 is lower, it's probably going to lose the 3 instead of gaining the 5. So we're likely to form a 3+ ion, and that is what we form. What about nitrogen, number 7? What kind of an ion would you expect to form from nitrogen? -3, right. So that's in 5A, which means 5 valence electrons. So it can either lose 5 and become 5+, or it can gain 3 and become 3-. So we're going to go with the gain 3 and get 3-. And so this way we can predict all of the charges on those sides of the periodic table, on the left and then over on the right. We'll get to the middle in a little bit. All right. What we can use that for then is to make compounds. An ionic compound is a positive and negative anion put together, or a positive negative ion put together. You can't just have positive ions. You can't just have a jar full of sodium ions. You need something negative to keep them in balance. So ionic compounds are something called a cation, which is a positive ion, and an anion, which is a negative ion, put together so that the overall charge is neutral. So you should have enough cations and enough anions so that together they end up having no charge at all. There's as much plus as there is minus. And sometimes this is easy to put together, sometimes it's not. So if we want to find the ionic compound that's made from sodium and chlorine, the first thing we do, I guess we don't really need not really a reaction. First thing we do is we write down the ion of each one that we would expect to make. So what ion does sodium make? We just did that. What kind of an ion? +1, right? So that's going to be our cation. What about chlorine?
Anion.
Yeah, and what number?
One.
-1. Do those charges balance, plus and minus? They do. So that means that our overall compound is going to be NaCl. Just one of each, they'll balance out. What if instead we make a compound of sodium and oxygen? Sodium is still Na+. What is the charge on oxygen likely to be? -2? Yeah, everybody see that? In column 6, so it needs 2 more electrons to be full, so -2. So now we can't just put those two together because it would not make 0. It would be +1 and -2. If we put one of those, one of each of those together, we get -1 overall. That's not okay. So what do we do instead, you think? How are we going to bring these two ions into balance so that we have an overall neutral charge?
Sodiums.
Right, we'll need 2 sodiums for every oxygen. So they'll need to make a compound that's a little bit different ratio, where we have 2 of those for every one of the oxygens with a negative charge. Does everybody see how that would work? So now you have 2+ for the 2-. When we draw that in a formula, we express that change in ratio by using a subscript number, which is a little number below the text. So it goes Na2O like that. And that tells us that for every oxygen atom, there's 2 sodium atoms in this compound. What about potassium and phosphorus? What's the symbol for potassium? K. By the way, when we do quizzes and exams, you'll get a periodic table that has the names, so you don't have to know all the names. You can look them up. What's phosphorus? P. What are the ions that K and P form? What does K form? +1, just like sodium. Everything in that column is going to be +1. What about phosphorus? Yeah, phosphorus is going to be -3 because of where it is over there in 5A. So how do you put a compound together with +1 and -3? Right. We're going to need 3 of the K's to balance out that P. So that compound is going to be K3P. One more. What about aluminum and oxygen? What's the ion of aluminum?
3+.
3 plus. And what about oxygen? We just did that one, 2 minus, right? So now we got kind of a problem because you can't easily balance those. If you add an extra oxygen, you now have 3 plus and 4 minus. If you add another aluminum, you have 6 plus and 2 minus or 4 minus. So what do? Right, you're going to need 2 of the 3 pluses and 3 of the 2 pluses so that the overall charge still works. And by the way, if you can't see that in these numbers, that's fine. You can still do this by trial and error. So you could say, okay, I have more aluminum than I have more positive charge than negative charge. So I need to put another oxygen. Well, now I've got 3 plus and 4 minus, so I need more aluminum. Well, now I've got 6 plus and 4 minus, so I need more oxygen. And now it works out. I've got 6 plus and 6 minus. And the way we would write that is Al2O3. When we make an ionic compound, we have to have an overall neutral charge. We have to bring them into balance. Okay. Feel okay about making ionic compounds so far? All right. Let's get to the next part, which is naming ionic compounds. We're going to do this in 2 parts. Put them right next to each other. So first, the easiest ones, when you name a compound that has fixed charge, which is everything we've been talking about so far. The next category, I'll put it over here to get ready for it. They have slightly different names for metal, for compounds where the metal, the cation has a variable charge. So these would be column 1A, 2A. Variable charge is everything else, so mostly 3B to 2B, that whole row, and actually some others. Let's make that more complete. The metals in 4 and 5A are also variable charge. All right, let's talk about the first one. That just means they can have more than one possible charge, so we have to talk about them a little bit differently. So if our metal is in 1A or 2A, we know what the charge is, and so naming these things is as easy as putting the words together with one little change. So our name is going to be the cation, and the anion, where you've dropped the end of it and put "ide." So for some examples, the ones we just did, NaCl, we call that sodium chloride. Na2O becomes sodium oxide. K3P, what do you think? Yep, potassium. phosphide. What else did we do up there? Al2O3. Aluminum also fits in this category, by the way. It only has a +1 charge. There's a couple more too, but I don't want to get everybody confused with exceptions, so we're just going to leave it at that. What would we call Al2O3? Yeah, aluminum oxide. The nice thing about having these specific rules is that anybody knows what compound we're talking about. Before this idea, every different compound would have a different name. So instead of sodium chloride, it would just be called table salt. And something else, and aluminum oxide is alumina. And there's all different names for all different ones, and you just had to know what everything was called. You just had to memorize everything. That wasn't really a good way of going about it, especially as more and more new stuff was being discovered. So people got down or sat down around the world and developed these somewhat standardized ways of naming things. So you follow the rules, everybody knows what you're talking about. What can sometimes be trickier in this category, before we go on to the next one here, is when you're given a name, you should be able to write down that compound, write down a formula for what that compound is. So if I said, if I said write a formula for lithium sulfide, you would do that by first writing down the atoms. So you'd look up lithium and you'd find sulfide you wouldn't find in your list, but you'd find sulfur. So that's probably close enough. So you'd write down Li and S. And then you can't just stick those two things together. You have to figure out what is the ratio that we need based on the charges. So what charge does lithium have? +1. And sulfide is -2. So how do we bring those into balance?
Lithium to sulfide.
Yeah, we need 2 lithiums for each sulfide so that we can have 2+ for the 2-. And then we can write down a formula, Li2S. Okay, let's look over at the other side now. What happens when you're trying to name these compounds with these metals in there? Like this. So here's why it's a problem. Here's why we need a different way of naming for these types of compounds. Both of those compounds exist, FeCl2 and FeCl3. They're both iron and chloride. So if we just use the naming scheme that we have over here, they would both be called iron chloride, but they're very different compounds. They're not the same thing. So that doesn't work. So we have to have a different way of naming them that shows that they are indeed different and shows us which one we're talking about. The old way to do it, which you may have heard before, is to say things like ferrous chloride versus ferric chloride. And that is one way to do it. But again, that requires a lot of just remembering which one is which and these weird new words and all this stuff. So now we do it in a systematic way that's always the same no matter what elements we're talking about. And here's how it works. We first figure out what the charge is on the metal that we're talking about. So to do that, we kind of break it down just like we did over here. Whoops, just like we did over here. And look at the pieces. So in this compound, we have 1 iron atom and 2 for every 2 chlorines. That's what that formula tells us. 1 iron for 2 chlorine. Now iron, we know, has different charges, but chlorine does not. So what's the charge on chlorine?
-1.
Yeah, it's always -1 for a chloride ion. So what must that charge be on iron then to balance that out? +2, right. So now we know that that is an iron +2 or 2+ ion. What's the iron over here then? If it's paired with 3 chlorides. plus 3. So our name is going to specify whether we're talking about iron plus 2 or iron plus 3. And to do that, we're going to write the cation and then a parentheses with its charge in it, and then anion. So for FeCl2, that's going to be iron. And what's the charge on iron in that formula? Plus 2. So we express that with a Roman numeral 2. And then we write chloride. And on the other side then, we're going to have iron 3 chloride. And that's how we distinguish those two compounds by their names. Iron 2 chloride and iron 3 chloride. All right, let's practice that a little bit. How would you name Cu2O? So the first step is to figure out the charge on the metal. Cu is copper. So to do that, I like to write all the pieces of the formula out. You don't have to. Let's do that. We don't know the charge on copper yet, but we do know the charge on oxide. What's the charge on oxide?
2-.
Yeah, we can get from the periodic table that it's 2 minus, because oxygen has 6 valence electrons, wants 2 more. So then what must each copper be in this compound? Plus 1. And then what must the name be for this compound?
Copper 1 oxide.
Right. So the name of this is copper 1 oxide. Okay. Be careful. The 1 applies to the charge. It's very easy to see Cu2O and call that copper 2 oxide because the little 2 is right there. You want to do that. But that's not it. It's copper 1 oxide. So to show that, let's draw copper 2 oxide. See if you can come up with a formula. What would a formula be for copper 2 oxide? So you can work that one out. Everybody come up with a formula? What'd you get? Right, CuO. So let's look at how we would break that down for those of you who didn't find that. First, we look at the name and we write down the ions. The ions present in this name are copper 2 plus, because the 2 is given right there, and oxide, which we know is O2 minus. We look at those 2 ions then and we try to adjust the ratio so that they balance. And here we see it's just 2 plus and 2 minus. So copper 2 oxide must be CuO. 2 plus 2 minus balances out. Okay. We've got a couple more minutes. Let's try a couple more. I'm going to write down a name and a formula you give me the formula and the name. If you don't have a periodic table that has names with you, cobalt is CO. And what's PB? You know that one? Lead. Lead. So see if you can come up with a formula and a name. Got some names? Formulas? All right, what do you got for cobalt 3 oxide? Can we get that one?
CO2O3.
Yeah. Well, let's put it together. We've got cobalt 3, which is cobalt plus 3, and oxide, which is O2 minus. So to balance those out, we need 2 of the 3s and 3 of the 2s. And that makes CO2O3. What about PbO2? What name did you come up with for that one?
Lead 4 oxide.
Right. In this case, again, we don't know what the charge of lead is. So we have to look at all the pieces, Pb and O. We know O is 2 minus. So to balance with two 2 minuses, which is 4 minus total, we need 4 plus. Whoops, that's not the name, that's just the formula again. So that's going to be lead 4, because it's 4 plus oxide. Sound good? Okay. This definitely gets easier with practice, so make sure you're doing lots of homework problems to work on this. On Thursday, we'll put in the last bit of this, which is the polyatomic ions with it as well. So if you want to look a little bit ahead, you can get started on that before the exam. I'll see you upstairs for lab.